The recording. Okay, thank you everybody for joining today. We are pleased to have Matt Chojnacki here to talk to us about multidirectional dune dynamics under seasonal winds on Mars. Go ahead and take it away, Matt.
Awesome. Thanks, Matt. Yeah, we just wanted to highlight a paper that came out in GRL last month, and I think the link was in the notification email for the seminar, but it'll go to this open source article where you could see the authors are listed there and their affiliations, where Isaac was the other PSI who helped with the mesoscale modeling along with his student Pruvi. So to give you a little context, bedform evolution under spatially variable winds has been looked at a little bit on Mars, but particularly for this study. We know that atmospheric winds frequently transport sediment across the surface of Mars today, as evidenced by the mobility of aeolian bedforms observed both from orbit and in situ. But in contrast to Earth, Mars exhibits often stable atmospheric forcing of sand pathways, partially due to the north-south crustal dichotomy and its tenuous atmosphere that really contribute to the frequent formation of migration of crescentic dunes. And you can see that in this top plot with barchan dunes in Oyama crater. Prior high-rise surveys of bedforms have often focused on these simple dune morphologies that are barchan or barchanoid dunes, because their displacements are in a single direction and they tend to be the easiest to quantify, since Martian dunes migrate at a slower rate than they do on Earth. Now, in comparison, some dune field dynamics are subject to multiple directional wind regimes, or whether they be orthogonal or converging, but have yet to be thoroughly investigated using high-rise until now. So this effort seeks to characterize and explain how Martian aeolian bedform systems evolve spatially under seasonally variable winds. The questions that we wanted to answer are, for these dunes influenced by multiple wind regimes, what are the variations in sand flux seasonality, and how does that compare with regional winds from mesoscale modeling? And then, can the influence of perihelion or aphelion periods, basin winds, or known storm track sequences be related to bedform dynamics? So to assess the seasonal behavior of select aeolian systems, we utilized high-rise ortho images, digital terrain models, and atmospheric modeling. High-rise, of course, is on Mars Reconnaissance Orbiter. So for morphology and long-term patterns, we wanted to look at sand dune azimuths, migration, and sand flux metrics collected in GIS measurements on long baseline annual observations. So 5 to 7 Mars years in all these cases. Meanwhile, to look at the sand flux variability in a shorter time frame, we looked at the ripple dynamics with COSI core measurements in seasonal ortho images. And then finally, to get an assessment of the broader seasonal wind patterns, we looked at atmospheric trends from the LMD Martian mesoscale model simulations, and that would give us insight into not only seasonal but diurnal wind trends. So here we are in our Hellespontus Montes. This is the, for context, this is the western rim of Hellas Planitia, the largest impact basin on Mars. And we really wanted to look at the diversity of these dune fields mapped here, where you can see Hellas Planitia, you see lots of dune fields, and then the rugged terrain in Hellas Planitia, and that gives way to kind of the plains in Noachus Terra, where there's lots of impacts craters with dune fields. And we've mapped two different kind of dune fields here. In the blue or cyan, we're showing you kind of these simple crescentic dune fields where they're just dominated by barchans or transverse dunes, whereas the yellow dune fields are shown to represent multi-directional dunes of star dunes or reversing dunes that just show a lot more diversity in their morphology. And for this work, we looked at two sites. The primary site is on the western, they're both on the western rim of Hellespontus, but you can see the yellow arrow shows this East Hellespontus site where early work, and I'll show you some of that, we saw dunes migrating east and west, whereas a second Hellespontus site 40 kilometers west is where these unidirectional barchans were migrating westward from their mesa source. And so here's kind of where we were at about in 2009 with a geology paper where we looked at East Hellespontus and found that these dunes were migrating both to the west-southwest, but also to the east-southeast. Meanwhile, there's star dunes and really complex interactions going on within the dune field. And all we knew was just that these outlying dunes were migrating kind of towards one another. Meanwhile, we went to West Hellespontus, and this is actually a really well documented dune field where there's just these beautiful symmetric barchans and linear dunes. And these are just migrating in one direction, just west to west-southwest, and very little evidence for that other wind direction that we saw evidence for at the East Hellespontus site. So for East Hellespontus, that's this top plot in B, we documented a diversity of dune morphologies, ripples, and megaripples that are migrating in these three different wind regimes. Wind regime 1A is kind of towards the west, wind regime 1B is a little more to the southwest, and then meanwhile, wind regime 2 is going to the east. And fluxes appeared to be a little higher on the eastern side, suggesting stronger westward flow. That's something that we noticed in the regional dune morphology and earlier looks at migration in the region. When you looked at the sand flux, this is a rose plot showing the three different wind directions, 1A, 1B, and 2. You can see when we mapped all the dune fields and then ripple patterns all within something like 7 or 8 high-rise images. That's all encapsulated in this one rose plot. You can see that there's just a lot of spread and diversity in their directions and their magnitudes. Meanwhile, in West Hellespontus, looking at the figure C, you can see that sand transport is driven solely by the westward winds, while eastward winds are not really visible. We saw higher migration rates at the West Hellespontus site because they're all going in one direction. And because of that, that causes drastically lower reconstruction times for local dunes, or the time that a dune takes to migrate across its own path and reorient itself if winds were to change. So something on 150 years versus 600 years at East Hellespontus is much different. You can see that the wind directions and sand fluxes are all kind of dictated in that narrow corridor that we showed. Looking at the seasonal ripple dynamics versus the mesoscale modeling, this plot kind of encapsulates a nice comparison. So looking at the plot B and C, that's all ripple mapping from seasonal high-rise images, where the top row there shows the temporal progression. You're going from left to right and forward in time, and we both have we go through Mars year 34 summer all the way through to Mars 35 summer over a year, and we saw that all three wind regimes are most effective at all three wind regimes are most effective at moving ripples in the summer and spring, the warmer seasons, and then there's a sharp decline. So you can actually see right in this winter that we had this one COSI core image pair that we were able to look at, but it was over a large gap all over the winter in late autumn, which had the lowest rates compared to these higher fluxes and ripple rates in the summer and spring. Now the LMD modeling, which is along this plot A, it showed steady, strong westward winds in afternoon and evening year-round, except winter. And meanwhile, we saw reversing eastward winds as well, but at lower rates. The westward sand migration is attributed to these daytime anabatic upslope winds out of Hellas due to diurnal heating of the Hellas basin during warmer seasons. And you can kind of see the seasonal variations in this plot, which again is showing solar longitude across the bottom. So it progresses from left to right as you go through a Martian year, while the azimuth of the mesoscale modeling results at the Hellespontus sites is shown here. So these are all downwind directions, if I didn't mention that earlier. But you can see that all the wind regime 2 is occurring in the colder times of the sol, so late evening or early morning, whereas the warmer seasons, warmer times of day are shown up with wind regime 1A and 1B, and that partially explains why they're more effective at moving sand in that time. You can also see perihelion period, this orange pattern is where you see most of the sand transport compared to winter and aphelion in that blue zone. So these are opposed to the more moderate eastward winds. Kind of mentioned that these are geostrophic driven westerly winds relate to the balance between the pressure and the Coriolis forces in the mid latitudes, but they're really further enhanced as cooler katabatic winds drained into Hellas overnight. And that's something you can see in these really cyclic animations. So this is just 3 days over 3 L-S periods, L-S 10, 310, 320, and 330. And these all go through one sol. And when you can see the warmer temperatures are the reds, and you can see at the daytime, those are the warmer temperatures, and those all swing to the west. And then at night, it swings to the east, and cooler winds are draining into Hellas each evening, but at lower rates, which make them less effective at moving sand transport. But there's other boundary conditions that are impacting regional aeolian bedforms and their transport. The eastern dune fields sit within a shallow east-leaning saddle surrounded by higher terrain, shown in A, where all the dune crests are broadly transverse to the local slopes. And we can see that in the simulated wind vectors. This is a basin, part of a basin that's being funneled by basin topography. We also know that there's seasonal volatiles at 40 degrees south and lower degrees. So CO2 frost is observed in winter images, and that can have a range of effects on bedform surfaces, as documented from other polar studies. The frost is concentrated on south-facing slopes where you're having some cold trapping effects, and that temporarily can stabilize some ripples, but also these steeper slopes like the slip face in the subplot in the top right. That's areas where you may have slumping due to the carbon dioxide activity that's going to cause some southward transport. So there's some impacts that the frost can occur. Now, at the western site, you've got totally different topography. You're within a crater. That you've got these barchans migrating across the bottom of the crater floor, but the broader topography shows that the Hellespontus Montes ridge is to the west, and that can influence some of those eastward winds in a way that it mitigates some of those westerlies. Meanwhile, you've got these mesas in this subplot 2 that show you can have some funneling of winds that really focus those the winds between the mesas and creates those long linear dunes and barchans that all migrate in one direction. So we saw simple and complex dune fields in Hellespontus Montes, where some were found to be subject to seasonally and directional variable winds. At East Hellespontus, long-term dune migration reveals 3 wind regimes for the west, southwest, and east that all converge in the center of the erg. These are all most effective during the summer and spring when the season's temperatures are warmest. Hellas Planitia slope winds, both daytime anabatic and nighttime katabatic, have a prominent role in that kind of reversing motion that we saw across the region. But those diurnal and seasonal cyclic winds can be highly localized, as nearby West Hellespontus barchans are just migrating exclusively to the west, and eastward winds are really mitigated by topography. Ultimately, it's this interplay of slope winds, local and regional topography, and surface frost that can highlight the complexity of dune field evolution on Mars. And with that, we can open it up to questions. Oh, yeah.
Bravo, Matt. That's really nice work. Were there any surprises in the work? I mean, you can see the dunes are moving, kind of converging at this site here in your primary image. Were you surprised by anything that you found?
I may not have highlighted it particularly, but I think your mesoscale models showing how you can see in the top plot A here. So those are just wind roses, and there's nuances that I skipped over, but some of those blue ones are below shear stress values needed to initiate saltation. So those blue petals aren't really moving sand a lot, but when you look at those rose petals, and those are all in the downwind direction, you kind of see a pattern that would suggest that it's really, there's a lot of eastward winds moving through the region, and that certainly is the case. They happen to be more frequent. It's just that the summertime, spring and summertime warm westerlies are more effective at moving sand to the west. So I assumed that we would see more rose petals that towards the west, but it's really, what's above shear stress and what's going to be most effective during the warmest times of year. Yeah. That was the biggest, I think, surprise to me, is when we first started looking at these simulations.
Yeah, thanks.
Anyway, we can go back to that stuff's what got me excited about this. Yeah.
So what's your next step? Your next research project along these lines?
Oh, along these lines? Well, I mean, basically I had a basic understanding of what we're seeing here, and I wrote a third of a proposal with Isaac's help to to come up with the paper that I just released. So this particular region, there's other things you could look at, but for sure, I'm interested in. I didn't really go over the next thing that we're about. Oh, let me see this plot here. 3 and 4, those little subplots, those are megaripples that are migrating in different directions. And I'm currently working on a paper to describe megaripples and transverse aeolian ridges that are migrating on Mars, which has been, understudied in some cases. But we'll talk a little about that in an upcoming paper for the reversing megaripples, but not much more in Hellespontus, at least at this point.
And are there paleo dunes on Mars? I mean, are there examples of dunes which are not moving at the expected speed or totally disagree with the model wind directions? So is there evidence for paleo dunes anywhere?
Yes, absolutely. Last year we had a paleo dune or paleo bedform survey published in Geomorphology. And that talks about mostly dunes and megaripples, but some other bedform classes that show evidence for being cemented, and they're pummeled by small impact craters. They've got boulders going down their slopes. Those are true cemented paleo dunes or paleo bedforms that are part of the rock record. But there's a large gradient from these active dunes that we saw in Hellespontus to those cemented paleo dunes that you can find in places like Melis Chasm. And that has to do with a lot with the volatiles. And I think there's some evidence for the South Polar dune fields to be largely stabilized. We don't see a lot of movement there, but that's something I'm interested in following up more. Good questions, thanks.
And the paleo dunes, do they follow a current wind direction, or is there a paleo wind direction, which is different?
It's complicated, but there's some areas where you could make an argument that the paleo dunes that presumably formed in the maybe the mid-Amazonian, so maybe hundreds of millions to a billion years ago, that those are oriented differently than modern bed forms that are nearby. But it's not always evident because you don't have those contemporary wind markers like wind streaks or active ripples in that area. Sometimes you have paleo dunes out in the middle of Apollinaris on the edges of that volcano. There's some fantastic paleo dunes, but there's no modern dunes within hundreds of kilometers. So it's kind of hard to make an assessment there. But it's a good discussion point that we went over in that paper.
Okay, well, thank you so much, Matt, for the talk. And thank you, everybody, for joining.
Thanks for throwing it together.
Mm-hmm.
Thanks, everyone, for joining. Cheers.
Okay. Thanks, Matt.